Hello, my name's Kevin Partner from our Pi Lab. I'm also the author of Raspberry Pi for Beginners. The point of this video is to help to introduce electronics to owners of Raspberry Pi computers. The whole point of having a Raspberry Pi is that it enables you to control and interact with real-world objects. And for most of that, you're going to need to use electronics. So why pick a flashing LED project as a beginner? Well, to begin with, why not? Who doesn't like flashing LEDs? But there's a more important point, which is that the technique that we're going to use, which is a very common technique in electronics, actually results in a timed output being provided by a particular timer chip. And that can be used for all sorts of things, including, for example, periodically triggering a sensor if you were creating something that measured soil, the amount of water in soil, for monitoring your plants, for example. Then you wouldn't want to be doing that all constantly, because it would be a waste of voltage. Instead of which, you would periodically trigger a sensor. And whilst you can do that from the Pi, why not, if you can, hive that off to dedicated electronics? You can also use the technique for powering a motor by very rapidly sending pulses. You can control the speed of a small motor for a robot or whatever. Or, what the hell, why not just flash a light? Who doesn't like flashing lights? Right, let's begin by looking at the parts that we're going to be using. Before we introduce the parts, I'd like to mention that my two favourite component suppliers, bitsbox.co.uk and coolcomponents.co.uk. Bitsbox has an electronic starter kit which contains everything that's included here, along with hundreds of other components. I don't have any connection with them, but I found their service and that of Cool Components to be very good, and their price is excellent also. Now then, the components that we have to use for this project are 9-volt battery and clip, a 555 timer chip. Now this was developed in 1971, which is an age ago in terms of electronics, but it's one of the most widely used chips in the world today, and this is the heart of our project. An LED, standard LED, any colour you like. We have here a 100 microfarad capacitor. We also have a 0.01 microfarad capacitor. We have a 220 ohm resistor for the LED to protect the LED, a 4.7k resistor, and another resistor whose value you can choose, because that resistor will determine the speed of blinking. In this case, I've just chosen another 220 ohm resistor. Okay, so we'll have a quick look at the chip, the 555. It's called that because it has three 5 ohm resistors. Let's begin by looking at the 555 chip. Now, all chips of this format have a little dent in the top, which you can probably just about see there. That's used for aligning the chip. If you place the chip in a solderless breadboard like this, with the dent facing to the left in this case, as I'm looking at it, you can number the pins now. So that is pin 1, 2, 3 and 4, 5, 6, 7 and 8 on this particular chip. Okay, so that's how we're going to number them. Now then, I'm using a solderless breadboard, which is invaluable for projects of this type. In case you haven't been introduced to these before, basically you just push components in. There's no soldering required. It has two sets of power rails. We're only going to be using one in this case, but you could put a completely different power supply in here. For example, you're powering a motor. You might want a higher voltage supply there and a lower voltage supply coming in here. I'm just going to use this one. And as you can see, you have plus and minus. Anything connected into any of these pins connects to all of them along here. So if I plug in my positive lead from the battery, that supplies power along all of those that are connected in red, equally obviously with the ground on this side. Within the body of the breadboard, however, the connections run down the columns here instead of across the rows. So each of these is numbered, starting at 1 and going along to 30. So if I were to plug in power to here, so I'm in column 30 there, that would supply power to all of these from A to E in this case. There's a gap here, so there's no connection between these rows, columns, and these columns. So we begin by placing our chip straggling across that gap. That gap's there so that none of these pins are now connected to each other. They're all isolated. We'll see how that works as we go through. So the way that this chip works is that you have two important pins, pin 2 and pin 6. Pin 2 is the trigger and pin 6 is the threshold. Essentially what happens is that when pin 2 is active, then pin 3, which is the one that turns the LED on, is also active. When pin 6 is active, then pin 3 has been turned off. The trigger and threshold are actually controlled by the level of voltage going into them. So while the volts are lower going into pin 2, then pin 3 will power the LED. When it reaches a certain point, the threshold, pin 6 is triggered and that turns pin 3 off. And we'll see how that works in a moment. But although there are 8 pins there, actually it's those two that are the most important. So let's begin with the easiest. We're just going to take a small bit of cable here and begin by connecting pin 1 to the ground rail. There we go. All pins, well, almost all chips will have one of their pins connected to ground and one connected to the source voltage that powers the chip. And in the case of this, the 555, pin 8 is the one that we connect to voltage. Actually, I'll just put it a bit further down. Put it there. There we go. Okay, that's the first two. Pin 4 in projects of this type is not. Pin 4 is a reset pin, so if you wanted to reset the chip you would interrupt the voltage to that pin, but we don't want to do that as part of this project, so we'll just connect that directly to the voltage, to the power. So that was easy. Now we need to connect pins 2 and 6 together because those are the 2 pins that monitor the voltage. So that's those 2. Hold on, I've put it in pin 1. Pin 2 and pin 6 are now connected together. I hope you can see that. Okay, we now need to protect, because pin 7 is the discharge pin. Now we're going to be using a capacitor to control the pace at which the timer chip functions, or it's one of the two things that controls that. What basically happens with a capacitor is that it takes a certain period of time to fill up. Capacitor is a bit like a bucket. It fills up with voltage, and the time that it takes to do that is part of what controls how fast the timer switch works. Once it has filled up and the threshold on pin 6 is reached, then the charge within the capacitor is then emptied again, so that for the next flashing cycle it can fill up again. What we need to do is actually protect the pin from the amount of charge that's coming out of there, because if you don't do that it might blow it and you'll have a broken chip. So we're going to use a 4.7K resistor, which we connect from the pin 6 column into the one for pin 7. In a minute. Oops. Protects pin 7 from the extra charge. We now connect pin 7 to the power rail via another resistor. Now this second resistor, I'm going to just bring it over here. As you can see, we can move across to make a bit more space. This second resistor is going to be one that we're going to use to help control the rate of flashing. So I'm putting it there so it's more accessible. You can see I've pulled across the power to there, and then put a resistor in the same row, column as this wire, which means that the power will flow into the resistor, or connect to the resistor there. And then we just need to connect that to the power rail. I'm going to put it down here so it's out of the way. There we go. Okay, so you should be able to see that pin 7, which is this one, connects via this wire to the resistor there, and the other end of the resistor connects to the power rail. Right, that leaves us with pin 2 to set up. This is the one that we're going to connect to the resistor, to the capacitor. So we move this over here. So you put a cable in the column for pin. You have to be a bit careful here, though I'm not connecting what I shouldn't connect. Pin 2. And you'll notice that capacitors they'll often have a grey or a black stripe on one side. This one, it makes it pretty obvious that it wants that to be connected to negative. That's off. Sometimes they have different length leads as well, but the safest thing is just to go for that. So that needs to be negative. This is a positive voltage, so we connect the positive end to that, and then the negative side straight to ground. There we go. So what happens here is that when the power is applied, the LED will come on while the capacitor charges. Once the capacitor reaches a certain point and the threshold is reached, the LED will turn off, the capacitor will discharge, and the cycle will repeat. Okay. So the main thing that's remaining to do now is to put the LED in. So as I said, the LED is powered by output 3, by pin 3. Oops, take a bit of a longer one, I think. So we'll bring that over here. Okay. We take 220 ohm resistor. That's to protect the LED, because otherwise too much current will hit it and it'll eventually burn out. An LED has two legs. It's the longer leg that we want to connect to this pin, and the shorter leg could plug it straight into ground, but I'm going to do it this way. So we've taken the output from pin 3, brought it across to here for convenience, passed it through a resistor to limit the current, into the LED, and then out to ground. There's only one thing we remaining to do, because you may have noticed that we have now dealt with pins 1, which is ground, and pin 8, well, pin 1 which is ground and pin 8 which is power, pin 2 and pin 6, pin 3 which is output, pin 4 which we just connect to power, the reset, and pin 7 which is the discharge pin. That just leaves us with pin 5, which is the control voltage pin, which we don't do anything with in this project. But so you could leave it off entirely and do nothing with it, but you'll improve the accuracy of the circuit by connecting it through the tiny capacitor to ground. What that does is it just protects it from interference from the rest of the circuit. Okay, and then what we need to do is just double check that everything is still in place after I've been fiddling with it. With those smaller ceramic capacitors, it doesn't matter which way round they go, by the way. It's only if it's indicated that you need to worry. That's in ground. Yep. Right, the moment of truth. At this point, we can now apply the battery to one end of the power rail. And fingers crossed. There we go. Okay, now I mentioned that one of the factors that influences the speed of the flashing is the resistor, which I've put here for convenience's sake. So let's try a different one. So let's ramp it up a little bit to a higher value. And when we take this out, you'll notice the flashing stops. Now hopefully you'll notice that that is flashing at a different rate to what it was before. If you struggle to recognise what the power of a resistor is, or the resistance of a resistor is from its colour bands, there's an excellent app called Electrodroid which I recommend for helping to identify them. So there we have it, our flashing LED. The other thing that affects the speed is the capacitor and how long it takes to charge up. Now then, one last thing which we'll try, just to demonstrate that this is more than just about flashing LEDs, is to ask the question what would happen if we removed this. Remember that this is just power being applied along there. What if, rather than an LED, we had a motor? Little DC motor, so we'll plug those in there, so that's power. Here's the motor. Put that into there. Oops. Hopefully you can see that that is now pulsing at the same frequency as the LED was flashing at. And I'll leave it to your imagination to work out the many uses you could put that to. Until next time, farewell, and don't blow yourselves up.